hit record. I think what happened last Tuesday is I didn't hit record, and that's why you don't have a recording for that.
I don't know because I found it about short circuiting this.
Yeah, don't.
I'm not touching that.
Okay, yeah. So potential energy. What is potential energy?
Potential energy.
How did you use it?
Energy possessed by a body by virtue.
No,
I don't know what this
no.
definition is.
I don't like that. So how did you guys use that one? Use potential energy. Okay, you had like gravitational potential energy, right?
What type of definition is
Where the higher up something was, the more gravitational potential energy it had, because it had more potential to fall down. Okay, so I think you did use one where I like stored.
Yes. I'm just
Okay.
trying to say like a part that stores up energy and has potential or something.
Excellent. So yeah, it's a type of stored energy into something that you attribute to some sort of interaction. So like gravitational potential energy, it was attributed to gravitational forces. When we talk about electric potential energy, we're going to correlate it with electric forces. And the definition for potential energy I like best is that the potential energy an object has is its potential to gain kinetic energy. Because I said just a second ago that the higher up something is, the more potential it has to fall. And I didn't mean that like it's more wobbly. What I meant was it will fall harder, gain more velocity and kinetic energy if it starts with more potential energy. Does that make sense? Okay, I got nods. Okay. Okay, so right now we've defined potential energy kind of in reference to kinetic energy. So what's kinetic energy?
How
Okay, so it has to do with speed.
hard can you throw an object?
How hard? There's one more thing that comes along with kinetic energy. Mass. Yeah. Okay. So good equation, 1/2 mv squared. And it's just the energy associated with movement. So if something's moving, it has kinetic energy, and you wouldn't describe stored energy as kinetic energy. You just describe, hey, this thing's moving, and so that movement has energy. Motion energy. Okay. Last thing I need you guys to define, conservation of energy. What does that mean?
They were all the energy from the system were always supposed to conserve.
Oh, I like that definition. Okay, so conservation of energy mathematically means that the initial energy in the system is equal to the final energy in the system. So if that's true, then your energy is definitely conserved. You generally hear it said energy can't be created or destroyed. And so that's a good one. I also really like that you were using the word system, because while energy can't be created or destroyed, it can certainly leave your system. It can dissipate in ways that you can't get it back. Like that sound, I'm not getting that energy back, right? So when we think of whether we should conserve energy or not, you definitely do need to think about your system and whether or not it's a conservative system. So what sort of things do you look at to say, oh, this system is conservative, or oh, this system is not conservative?
Oh, yeah, that.
That marker, is that marker's energy conserved?
Yes.
I like the no. Why are you saying no?
Stop, slow down.
Thank you very much. I
I
appreciate
conserve the energy.
it. Excellent. Okay, the energy of you plus the marker. I'll call it conservative. But yeah, you said it was going to slow down and stop, right? What was going to cause it to slow down and stop?
Gravity.
Friction. I like friction. Okay, so friction, yeah, systems with friction, they're not going to be conservative because friction is a force that doesn't store energy. It dissipates energy. As opposed to gravity, which is a force which does store energy. So like if gravity causes something to slow down, like if you throw something up, gravity causes it to slow down, but it stores that energy because that thing will then fall back down and the potential energy will get transformed back into kinetic energy. Okay, let's think of our systems that we have dealt with so far. So far we've dealt with very abstract, we put some charges in a vacuum, or we have some metal object. How do you think friction is going to play in these systems?
Take away.
It could take away. Do you see a lot of sources of frictions in these imaginary systems we've been making up? No, right? Because we've been kind of careful to be like, okay, it's like an empty space and there's some charges. So no, we're really not going to consider friction in this class. You really don't even want to consider friction too much until you hit like quantum mechanics, and then there's like a whole different thing to deal with it. But usually in electricity and magnetism, you just don't worry about friction at all because it's so negligible compared to everything else that's going on. Okay, so for this class, just consider that energy is conserved. Okay, so let's look at a system that we've been used to. So I have an electric field. It's going to the right. I'm going to put a positive charge Q in this field. It's going to experience a force. Which way is this force going to point? To the right, along the field, because positive charges want to go with the field and negative charges want to go against the field. Okay, so it's going to feel a force that way. Newton's second law being what it is, it will accelerate to the right as well. So it'll accelerate to the right. That means as it's running down this field, even if I drop it in with its velocity equal to 0, by the time it gets over there, it'll be going very, very fast. So far, so good. So looking at this picture over here, this thing has a lot of kinetic energy. Over here, when its velocity was 0, it certainly had 0 kinetic energy, which means this kinetic energy must have come from somewhere, and clearly it must have come from potential energy. So we need to figure out some potential energy, like the potential energy of electricity, to figure out where this came from. Everyone pretty happy? Let me ask you a question. As this particle is going from the left to the right, is it gaining potential energy or losing potential energy? Losing, right? Because you're gaining kinetic, so you must be losing potential. So if we think about how the potential energy is changing, it is negative. And we are going to use an equation of work to figure this out. Do you guys remember work? What? Okay, yeah, no, this is really good. So work was equal to force dot displacement, and I'm going to write it as an integral because we're going to want integrals. So instead of just f dot delta r, we have f dot dr, and you're just integrating over whatever path you have. Okay, what do I say? Work, that. Okay, and also if you remember, like when work was first introduced, we really talked about work as a change in energy. So work is how energy changes. So here's the goal. I need some sort of equation for potential energy of electricity. So I am going to define myself a system where I can see energy is changing. And then I'm going to calculate how much work has gone on. however much work has gone on is going to be equal to the amount of kinetic energy that has been gained and also the amount of potential energy that has been lost. So if I can write down an equation for work in terms of things like electric fields and electric charges, that will probably be my equation for electric potential energy. And you guys have almost got me there, because you told me that I'm looking at a force dot displacement, right? And so instead of a gravitational force or a spring force, let's just put an electric force in there. The electric force between a charge and electric field is that charge times the electric field. So we can make that substitution. Dr. Sorry, my E's got a little messy there. E.dr. And I'm going to move this minus sign over there just for fun. Okay, and I'm going to circle this, and we're going to talk about it for a while. Okay, so here's a good, just like, starting point for electric potential energy, where we can, if you have an electric field and you're going through a path, I have Ri and Rf, where Ri and Rf are just the initial and final positions of this thing, you know, like whatever path you're going through. And you could integrate this. So in general, like this is a good just definition of what electric potential energy is. Now I'm going to write it slightly differently because I should have from the beginning. Well, not the beginning, but like right there, where I'm taking that electric charge and I'm putting it right outside the integral, which I can do because it's a constant, right? Maybe my electric field might change, but my electric charge shouldn't. And so we do this thing in EM where we like to separate the interaction from each particular component. And we did that when we were talking about fields and forces, where the force was K Q1 Q2 over R squared. And then we said, well, why don't I just pull off one of those Q's? And so I'll have the electric field is equal to KQ over R squared. Because I wanted to talk about the electrical properties of one charge without having to worry about the interaction. I want to do the same things here. I have this field, which is doing something electrically, and I have this charge, which is interacting with that. But I want to talk about just what this field is doing electrically. So I'm going to pull off all the components that just have the field in it, which is this, whatchamacallit, this integral, and I'm going to call that something. And when I say I'm going to call that something, clearly, I mean someone else decided to call that something. And so, let me write this down. So R initial to R final. Okay, this is an electric potential difference. It is a terrible name because you will hear the word potential, electric potential, and electric potential difference all kind of used, switched out a lot of times, but they mean different things. So electric potential energy is the interaction between two things. In this case, a charge and electric field. Electric potential difference is the properties of just one thing. In this case, just the electric field. Different things, except a lot of times you just hear the word electric potential. Most of the time that means electric potential difference. Occasionally, sometimes some will mean it to be the energy. I'm sorry, it's confusing. The trick to it is to know, like, electric potential difference means one thing. So you can't, and electric potential energy means two things. So you can't find the electric potential energy of just an electric field. And you can't find the electric potential difference of two charges interacting. And so you kind of have to take your cues from the question that's being asked. Okay. Let's put down some units here. Energy. What are the units of energy? They are joules. Or just J. For electric potential difference, the units are volts, which also confusingly is just a capital V. So occasionally you say a potential difference delta V is equal to 10 volts with also a capital V. Yes?
What's the difference between joules and volts?
The difference between joules, excellent question. The difference between joules and volts is that extra charge. So a really good equation to have is that your change in potential energy is equal to a charge multiplied by a change in potential difference. And so if this is joules and this is volts, this is a coulomb. So joule equals a coulomb times a volt. Or a volt is a joule per coulomb, also valid. I'm going to write that over here. Joule per coulomb. And so let's talk about, oh, there's one more thing. Vectors are scalars. Is energy a vector or a scalar? Looks like a scalar. One trick to see is that you have a dot product, and a dot product takes two vectors and gives you a scalar. And so once you've taken a dot product, you've gotten rid of directional information. So potential energy, scalar. Just so you know, potential difference, also a scalar. And these are deltas, so like you can gain energy and lose energy. And when you lose energy, you'd say negative. But that doesn't refer to a direction, that just says you're losing something. Okay. This is pretty good. What else? Okay, and I did want to talk about this for a second, because one unit that you are going to see is an electron volt. Electron volt, also known as just an EV. And an electron volt is the work it takes to get one electron through 1 volt of potential difference. And it is equal to 1.602 times 10 to the negative 19th joules. Okay, and so let's look at that really quick. When this charge is going down this electric field, the electric field is pushing it, right? So the electric field is putting energy into this electric charge. The amount of energy it would take to get an electron to move through 1 volt of potential difference is this 1 electron volt, where you notice an electron has units of coulombs, a volt has units of volts, and so you end up with joules. And so this is a kind of weird unit because it's electron volts, but it's actually a unit of energy that you can refer back to joules. Okay. And you know, I think, ooh, and you know, let's there's one more set of equations I want to get out. Okay. There's actually several sets of equations I want to get. It's the easiest set of equations. Let me start. Let me start here. Okay, here we go. because potential difference and electric field. Okay, so let's talk about potential differences in electric fields, because now that we've have this picture and we separated out the charge, I just want to look at what's going on with this field. So I can talk about the potential difference of this field without having to put a charge in it and think about what a charge is doing. Well, one thing I know is that I have just, like, by definition said that a potential difference, really, I want to say ds. I'm gonna say ds. Okay, there's a reason I did that. So by this is just, like, by definition what a potential difference is, where the potential difference is this integral of electric field with respect to space. S is like an arc, like just a general position. By calculus, of course, we can flip this around. Instead of saying volts are the integral of electric field, we can say electric field is the derivative of potential difference. And if we did that, what we would get is that the electric field is I'm going to put it this way, is the derivative of space. We're gonna talk about my weird symbols first, but first I'm going to put a minus sign on it because I have a minus sign there. And I'm also going to put a direction on it because my electric field is a vector and not a scalar. Okay, let me write this nicer, where instead of having generalized coordinates like I have there, I can say that the electric field in the x direction is the derivative of the potential difference with respect to x in the x direction. And the electric field in the y direction, the derivative with respect to y in the y direction. And same thing with the z direction, because this is a very three-dimensional course. So however much the voltage changes in one direction, that's how much the electric field is going to be in one direction. So another way to say this is that your electric field is the magnitude of the rate of change of your voltage. There's a lot of words there, but let's look at this this picture here. My electric field, let's say it's 1 Newton per Coulomb here, so 1. That is also equal to 1 volt per meter. And if you look at the equations I have here, I have volts over space. So our other units we're going to have for electric field are volts per meter. Okay, so volts per meter, I'm kind of hoping you see that as very much a slope. So for every meter you go forward, your voltage is going to change by 1. Also note that you have a minus sign. So that means that your electric field is pointing towards lower potentials, not higher potentials. Make sense? So say we start off over here at 10 volts. If we go over by 1 meter, we will be at 9 volts. And so on down this line. For every meter we go over, we drop one voltage. 1 volt, I should say. And so if you had a graph of potential difference versus position, potential difference versus position, the slope of that graph would be your electric field. Okay, everyone kind of happy with that? And what's more, is everyone kind of happy with that being what these equations say? So these equations say that the electric field is the derivative of voltage with respect to position. And so that means that they should be the slope of the volts versus position graph. Do I need to pause to let that sink in, or can I go on to the next thing? I can pause. And I can repeat ad infinitum. And I would make sure that everyone understands that you do need a minus sign there. So if you have a negative slope, you have a positive electric field, and a positive slope means a negative electric field. Okay, and I would like to take a moment to talk about these symbols that I've written down, because you notice with my derivatives, I haven't been writing down d's. I've been writing down these partials. I think I might have mentioned them for all of 5 minutes last semester. Has anyone done a partial derivative here? No, okay, let's talk about partial derivatives. So clearly we can have a very three-dimensional sort of space, right? So I can have a voltage in terms of x, y, and z. So maybe I have like 2x in the x direction and 3y, z in the y direction, and nothing in the z direction, like that. And we can have this because if you have a charge, it's not putting out a field in a plane, it's putting out a field as a sphere. And so most of the picture I draw are two-dimensional because I have a flat surface to draw on, but this is very three-dimensional. So when we start taking derivatives, we need to not just think about what's happening along the horizontal, we need to think about the vertical and the z direction as well. And when we say the derivative, let me leave off the minus sign for a second. When we say the derivative of v with respect to x, what I'm saying is I want to know how this is changing horizontally, because maybe it's constant in the other direction. Maybe like it's constant all this way, but it changes this way. And in that direction, if it's constant in this way, I wouldn't expect a big electric field that way because nothing's changing. But if it's changing in this direction, okay, that's where I expect to see an electric field pop up. Okay. And so if I want to take the derivative of this with respect to x, I would first off ignore the z direction because it's multiplied by 0. And second off, I would perform it like I would do any other derivative, where instead of having everything inside my parentheses, I'll split it up into 2 different problems. And then I'll take the derivative of 2x. And so what's the derivative of 2x with respect to x? I think I heard 2 out there. Okay. And you just kind of carry that x hat around. Remember, it's got a magnitude of 1. It's just a constant. And now here's the more complicated parts. Sorry, that's a, oh wait, this is an x. I'm just doing the x component. Good for me. Now I'm taking the derivative of 3yz with respect to x. It's simpler than that even. Because with respect to x, so if you're moving along in the x direction, are you changing in the y direction? In the z direction? It's just 0 because with respect to x, y and z are constants because they're orthogonal, right? And so if you're asking the derivative with respect to x as how does this change with respect to x? And if there's not an x in it, it doesn't change with respect to x. So it's 0. Is everyone okay with that? So just in general, this is how partial derivatives work. If you're taking the derivative with respect to one variable, treat all the other variables like constants. And then you just do regular derivatives. Okay. Okay, so for this voltage, the electric field in the x direction will be negative because remember we had a minus sign in our derivative. 2 volts per meter in the x hat direction. And then you'd go through and you do this for the y direction and the z direction as well. What else do I need to say here? Oh, I do need to say this. A lot of times you're going to see this shorthanded as the electric field is the gradient of voltage. All that means is add up all these derivatives in all the directions. I actually don't know how our book does it, but if you ever see this upside down triangle with a little vector, you can substitute that in. So that's what that means. People just don't like writing it out because it's really long. Okay. Okay, is everyone okay with that? Excellent, excellent. Okay, you guys are good with that. There's how much more do I need to get through before I can do the problem? Okay, so that was calculus. Let me do like what about if you have a constant E field? Okay, let's go back up here. So up here, I had a constant electric field, right? All my lines are parallel. It was constant. But we put it in an integral just to be the most general because maybe you'd want to apply this to non-constant electric fields. Okay. However, if you wanted to take this constant electric field and you wanted to perform an integral E dot dr like that from 0.1 to 0.2 like that, would you need to split this up into little chunks? Or could you treat it as a whole? So as a whole, good. Because as you went to different spaces, you wouldn't be multiplying dr by a different electric field. It would just be the same number. It would be E naught times dr plus E naught times dr plus E naught times dr. Or you could take that E naught outside and just say, add up all my drs. Oh, yes.
So especially 2 points, well, isn't it still the same? It's constant electric field.
Excellent. So the electric field is constant. So we'd have a situation like this, right? Where the slope of this line is just a constant, it's just a number. And so if we want to know how much our voltage has changed throughout there, we take this slope and we multiply it by the displacement, right? And that will give us the amount that the voltage changed. And that's actually what I'm trying to say, what I'm getting to over here, where our voltage E dot dr is really whatever that constant is times that delta x, right? And so yeah, whether you look at the graph or you look at the integral, you end up at the same spots. So if you have a constant electric field, you can use, so if you have a constant electric field, you can just use this equation that we have here. It's a really good equation because a lot of times in this class, we are just going to use constant electric fields. I put a D in there instead of a delta X because I didn't want to constrain myself to the X dimension. So any distance. You also see this written a lot of times as change in voltage over change in position. So again, if you have a constant electric field, maybe you don't want to do derivatives. Maybe you just want to say change in voltage over change in position. It gets a lot easier if you do it that way. Keep in mind that there will be directions on that. Okay, is that all good? Excellent, excellent. Okay, now let's stop and do some problems because that was a whole lot all at once. And surely I have some good problems to work on. Maybe I need to derive one more. Surely I don't need to derive one more equation. No, I don't. There we go. Okay, so let's start doing some problems because that was a lot of information. Start with number 3. Okay. Number 3 says consider 2 points in an electric field. So we got point 1 and point 2, and there's an electric field in here. The potential at point 1, 21 volts. The potential at point 2, 150 volts. Okay, so first off, I'm gonna vaguely draw an electric field in here. Should it be pointing to the positive X direction or the negative X direction? So do electric fields point towards lower potentials or higher potentials? And I'm towards the negative. And so this is actually a big thing. So let's make sure we have it embedded in our heads. Looking at this, my electric field points towards the right. As my positive charge goes along the electric field, it loses potential energy by going to lower potential differences. So if you're going along with the field, you're going to lower potential differences. If you're going up the fields, and this is kind of why we say up the field versus down the field. If you're going up the field, you're going to higher potential differences. Down the field, you're going to lower potential differences. So, well, I don't know like what shape this electric field looks like. It goes that way. Now we're going to take a proton, positive charge, proton, and we're going to move it from point 1 to point 2. And we want to write an equation for the change in electric potential energy of that proton. Sound good? Okay. Looking at this, do I need to know the length between those two spots? No. I like the no. Because the one equation that we have at this point to talk about potential energy in terms of potential difference is Q delta V, right? And it really doesn't matter if you have if they're really far apart or really close together. We're kind of trained to think that way because we're trained to think in terms of friction. Like if I roll something, it really matters the distance it goes because I've got friction at every point. But we're in a very frictionless area here, so they can be far apart, they can be close together. The only thing that matters is the amount of potential difference they're going through. Okay, just so you know, this program right now, it's going to take take E as the electric charge of a proton, because that's the electric charge of a electron, and they're the same charge. So for the equation, we just want E and then delta V, so we want V2 minus V1. Straightforward, right? So that's how much, when you plug your number, that's how much energy it takes a proton to move through that particular potential difference. Now here is something kind of fun. Part B, we want an actual number. So let's think about this. And let's think about this in terms of this very useful but elusive unit, electron volts, where this is the amount of energy it takes to move an electron through 1 volt of potential difference. And you got it by multiplying the charge of an electron by 1 volt. The charge of a proton and the charge of an electron are the same, right? So it's going to take the same amount of energy to move a proton through 1 volt of potential energy as well. I'm sorry, potential difference as well. So one way to calculate this is you plug in your 150 volts minus 21 volts. And so that'll tell you how many volts you've got to push this proton through. And then multiply that by an electron volt. Does that make sense? Okay. The electron volts. And that's just the answer. Sound okay? So if 1 electron volt is how much energy it takes to move an electron through 1 volt, 129 electron volts to move your electron or proton through 129 volts. It's a very useful unit that way. Also an interesting question. Then part C, we're going to ask how much work is done by the electric force versus during this process. Okay, so let me ask you a few questions. So we're looking for the amount of work being done. Okay. Does the electric, and we're looking at the amount of work being done by the electric force. So our field is pointing towards the negative x direction. Which way is our electric force pointing on this positively charged proton? So does your proton want to run down the field or does it want to run up the field? Down. So force equals charge times electric field, right? So if your charge is positive, the electric force will be in the same direction as the electric field. So as this proton is going through whatever it's doing, it's experiencing an electric force in that direction. Now, given that, is the work that the electric force is going to do, is that going to be positive or negative? And what you might want to ask yourself, is this electric force helping the motion or is it hurting the motion? So my proton's going this way, right? So yeah, it's hurting. So something else is moving this proton. So like someone has picked it up and moved it themselves. Some other force is moving this proton, and they have to do that because the electric force wants it to go the other way. So whatever work the electric force is doing, it will be negative. I'm going to put a minus sign out there. And you can kind of see that come out with the fact that the work being done will be equal to the negative change of potential energy. I don't know if that's, no, let me, is that the best way to say it? I think it is. Yeah, I think it is. Yeah. Where we calculated the change in potential energy to be 129 electron volts. And so the work the electric field is going to do will be negative 129 electron volts. And I'm pretty happy with that. Did that make sense? Okay, you like that. Okay. Let me say, so we calculated the work to be negative, right? What about the change in potential energy? Is our proton increasing in potential energy or decreasing? Increasing. Because as it goes from a low to a high potential, that's like raising something up higher against the floor. Like someone has to do that, right? Like gravity is not going to make something go up. So I'm putting something up. And as I do that, now it has more potential energy than it did from down here. And that's what's happening here. The proton is being moved towards a higher potential energy. And so whoever's doing that work is doing positive work. But the electric field is trying to prevent that. So the electric field is doing negative work. Excellent. Okay. Let me ask you, if we had put in an electron here and gone that way, would the electron's potential energy increase or decrease? Decrease. Awesome. Because that the electron wants to go up that field. Good question. Good answer, I should say. Okay. Okay, so far so good? Everything making sense? Because if so, I think I have time to get through this derivation. And after this derivation, things start, lots of things open up. So the thing I'd like to do now is I'd like to look at the electric potential. So this is electric potential differences due to point charges. Okay, so far we've looked at electric potential differences due to electric fields. But at some place there must be some charges making those electric fields. And so now I just want to say, okay, if I have a charge, what sort of electric potential will it make? So let's start with just, I have a charge, Q. It has an electric field. It makes an electric field, like so. And I have two spots here, and spot, A, spot B. And I'm just going to go from spot A to spot B. And I would like to think about the potential difference between A and B. Okay, I drew it with wiggly lines because I want the most general thing that I can figure out between these two. Well, I know I have this one equation so far for my potential difference. It's the integral of the electric field dot ds. Where ds is, I could split up this path into a bunch of little ds's. What can we say about the electric field due to a point charge. Do we have an equation for that? And if so, do you remember what it is? It starts with K. And if you don't remember what it is KQ over R squared.
Of course.
Yes. So we have KQ over R squared. And this was in what I'm going to call the R hat direction. Right? So it was pointed out radially. And so R hat means point out radially. And now we have to do this dot product between the radial direction basically away from the charge and ds, which I drew it really wiggly on purpose. And we can draw it as wiggly as possible. So all my little ds's might be pointed in all different directions. But let me ask you a question. My electric field goes that way. And if I look in particular, I know I'm not supposed to add extra lines, but let's look right there. Right there, my ds is going that way. Where I've tried to draw these two things so they're perpendicular to each other. When you take a dot product of two perpendicular vectors, what do you get? 0. Awesome. So any ds that's perpendicular to my electric field is automatically going to drop out of this integral. And even if it's just partially, the dot product's only going to pull out the part of the ds that's in the same direction as the r hat vector. Which means that, bless you, yeah. You can just get rid of the ds and say dr instead. And that's because ds might be dr plus some other part, but the other parts are going away. And now this integral is starting to look kind of friendlier, right? So k, is that a constant or a variable? Constant. How about q, the charge in the center there? Constant. So those two things are going outside this integral. And I'm going to be left with 1 over the integral of 1 over r squared. And what is the integral of 1 over r squared? Negative.
Or negative 1 over r.
You're perfect. Perfect. Excellent work. R b negative 1 over r, because that's r to the negative 2, add 1, you got r to the negative 1, pull that out front. So negative 1 over r. Notice really quick, I removed a and b and just called it ra and rb, because I want you to think about this in terms of there's ra and there's rb. So that's a good point of reference to talk about where a and b are. The minus signs cancel out nicely. And so we have KQ 1 over RB minus 1 over RA, which doesn't look like much until you say, well, that's equal to the change in voltage between A and B. And we can write this in a very suggestive sort of way. KQ over RA, where this is really the voltage of B minus the voltage of A. I'm hoping at this point you say, well, this is, I can say, well, the voltage of B is really that thing. And the voltage of A is really that thing. Okay. And so in general, the voltage of a point particle would be that. And let me call it potential difference, because that is more correct. difference of a point charge. Okay, units here are volts. Do I need to put like an R hat on this?
No.
Like the nose, because it's a scalar, right? So I don't need any sort of direction to it. Very nice that way. And I could of course like add up more than one if I wanted to. And I'm not going to get that into that too much this today. But if I had two, I had like Q1 and Q2, and I wanted to say, well, what's the potential of the area? I would definitely do voltage 1 plus voltage 2, KQ1 over R1 plus KQ2 over R2. And we would continue on, and we will continue on from there on Thursday. But before we do that, what might be more fun to do is to talk about potential energies of point charges. Since we just figured out potential differences of point charges, let's jump straight over to potential energies of point charges. Of point charges. Because we know that potential energy is Q times delta V, right? And so now that we have an equation for delta V for a point charge, we can now say, okay, what if I have 2 point charges? What sort of potential energy are they going to have? Let me draw a picture really quick. Q2. And say, okay, I have these 2 point charges here. I put them next to each other. Let me put them a little closer to each other. When I let go of them, what is going to happen? Yeah, they're going to repel. Okay. And for ease of use, I'm going to say I'm going to hold Q1 still, and I'm going to let Q2 move. And in the past, we've talked about this as being a repelling force. Another way we can talk about this is Q1 is putting out a potential difference equal to KQ1 over R. And Q2 is just rolling down that potential difference. So I could think about this being R1 and Q2 moving away to some other distance, R2. It'll really move in a straight line, but I can't draw that very well. And so I could think of the potential difference due to Q1 between these 2 spots. And that would just be V2 minus V1, or KQ over R2 minus KQ over R1. Make sense? And so those are just the 2 potentials from Q1. And if I wanted to know the potential energy between these 2 things, I would just multiply that by Q2. KQ1 over R2 minus, KQ1 over R1. Like that. And I'm going to say even more stuff here. This is a change in potential difference, right? Change in potential energy, where they start at higher potential energies, and as they move apart, they lose potential energy. So you can write this as U2 minus U1, KQ1, KQ2 over R2 minus KQ1, KQ2 over R1. And we would do the exact same thing we just did. we'd say, well, this would be the potential energy at position 2, their final position when they're further apart. This would be their potential energy at their initial position when they're closer together. And so in general, we could say that potential energy of 2 point charges was equal to K Q1 Q2 over R, where R is the distance between the 2 point charges. Okay, K Q1 Q2 over R. Where R, if you have 2 charges, R is the distance between them. Measured in joules. And do I need to put a vector on here? No, because energy is a scalar. Okay. Okay, that was, again, kind of quick. Anybody want to ask a question? And if you don't, let me ask you a question. What if I had 3 particles? How would I figure out that potential energy? Add the third part. Okay, let me ask you the question that I'd like you to answer using dimensional analysis. Would I just multiply in the third charge like that? No, I like that. I need the new R. So yes, that won't work, right? Because then I'd have an extra coulombs running around. What's really truly irritating about math is it's really good at 2 bodies and it's really bad at 3 bodies. So if you are 1, 2. So if you have more than 2 things, what you have to do is you have to approach it as a bunch. 1, 3. As a bunch of 2-body problems, and then you have to add them all together. R2, 3, R1, 3. Okay. So yeah, and then if you want the total, you just add all these 3 together. There's actually a really good book about 3-body problems. I don't know if I want to say anything about this.
Just keep it quiet.
Yeah. Maybe there should be. The question I would ask is, like, if I had 5 particles, how many potential energies would you have to figure out and add together? That's the question I am going to ask. Okay, what if you had 5 particles? 1, 2, 3, 4, 5. How many of these sort of terms would you have to make? It is it's not 25. And to answer this question, you need to answer another question. You notice I had like Q1, Q2. Did we have a Q2, Q1 term in here? All right, because without direction, it doesn't matter. So it doesn't matter which one you pick first. Say again?
Just stare.
It is 5 times 4 times 3 times 2.
Oh my gosh, yeah.
Yeah, it's one of those, like, if you have 5 things and you can choose 2, you always have. No, you're right. I'm sorry, because we're only choosing 2. It is 20.
You disregard the
Yeah, because we're only choosing 2. So you have 5 choices for the first one, and then you have 4 choices for the second one.
I just thought of it as 5 squared minus 5 since.
Oh, that's perfect. Yeah, because you get rid of all the doubles. Okay, excellent, excellent. Okay, I I am going to wrap this up. Next time, we're going to talk about equipotentials, and we're going to do some integrals. And come with any homework problems that you want to look at. There's a couple in here with integral, like we're definitely doing number 19. And it'll be a really familiar one. But if there's any particular problems you want to look at, let me know.
It's not about
Yeah.
it's not about homework. I mean, yeah, it is. So I was talking to people on the classes where it seems like people read and try to do the homework before we cover the chapter.
Okay.
Should we do that? Or?
You should do whatever works best for you.
Okay.
Dude, you did not see the amount of homework we have for
Yeah.
SPK this time. We
There's-
gotta have to.
Uh,
How many questions is that? That is